Hello and welcome back. So what I want to talk to you about in today's LTspice tutorial video is how to create simulation models for components and how to bundle up multiple models into a single library. So to create a single library that can cover more than just one component. And in particular, what I want to cover is vacuum tube diodes. Why? Well, they're quite easy to model compared to other things. And what I want to do is create a library that contains multiple diodes like this. The only difference between them being certain parameters that the original base model can work with. So if you're curious about how I can do that and much more, then keep watching. So the very first thing that you want to start off with when modeling any sort of component is actually understanding how that component works. See what are its quirks, what makes it special. And for that, I set up this little experiment right here. So what I got here is a sine wave coming in from the signal generator, getting rectified one time by a semiconductor diode, so the 1N4001 in this case, and then supplying a resistor, 10 kilo ohms. And on the other side, I'm doing the exact same circuit, but replacing the semiconductor diode with a vacuum tube diode. So the EAA91, small signal vacuum tube diode. And now, if we look at the waveforms in the two cases, we see how the two types of components behave differently. So the first thing we can see here, with yellow is the input signal, and with blue is the output signal in the case of the semiconductor diode. And we can see that when the voltage first turns positive, there's a bit of a delay between the input and the output voltage, and that is caused by the minimum voltage needed to turn on the semiconductor diode, so roughly 0.6 volts for silicon diodes. Then at the end, when the diode stops conducting, we see this little glitch going on, which is basically reverse recovery. So the silicon diode doesn't stop conducting all of a sudden when the voltage turns negative. There's a bit of a delay. Now granted, there are better and worse diodes for this, and in this case I'm using quite a bad diode at quite a high frequency. So that's why this effect is so obvious. Now with high speed switching diodes, this will not be as easy to notice. Now if we move to the vacuum tube diode, we see that our waveform is a bit different this time. So the vacuum tube diode starts conducting instantly, so once the voltage turns positive, it will conduct. There's no sort of threshold voltage needed to get it to conduct. We still see that there's a bit of voltage difference between the input and the output signal, and this is because of the voltage drop on the diode. And vacuum tube diodes are notorious for having quite large voltage drops on them, especially at high currents. And for vacuum tubes, high current means 10 milliamps. And at the end, when the voltage turns negative, we see no glitches. So the vacuum tube diode doesn't have this conduction in both ways. So no matter what you do, it will not conduct the other way. Okay, so that's about how the components work in real life. Let's see what sort of information we can find in the datasheet that we will want to include into our model. So what I got here is the datasheet for the EAA91 made by Philips. So as I'm going through the datasheet, I will also be working on the model in parallel. So the first thing to add into the model, since we're talking about diodes, are the two pins of the diode. So the anode and the cathode. Now here they named the anode D, but that doesn't matter. So I'll be starting off by adding a couple nets and assigning A and K as their names, so for anode and cathode. Next, so if we look through the datasheet, we see some information about the heater. So for vacuum tubes, having a heater is mandatory, but this is something that I will not be modeling. Next we see the characteristic curve of the diode. So basically what this curve is telling us is what current you're going to get through the diode based on the voltage between its terminals. And this we will add into our model as a behavioral current source. And now in this formula, we can specify that the diode only works one way and not the other. So basically, we can compare the voltage between the anode and the cathode with 0, and if we have a positive voltage across the terminals, then we will have a current, so we will have a formula here. If not, then the current will be 0. And basically, this is how we can model the diode's rectifying capability. Now, let's see what else we have in the datasheet. Well, right on the first page, we have certain capacitances. So we have between the anode and stuff, we have between the cathode and stuff. So it's not clearly marked here what to all means. But I did find this other datasheet, which is for the EB91, but basically it's the exact same tube, only this datasheet was made by Muller. And here we have basically the same capacitance values, but here it actually specifies that it's between the anode and the cathode and the heater and the shield, and the same way for everything. So to clearly understand where these capacitances are coming from, we can look at how the vacuum tube is actually built. So you may remember this from my old vacuum tube teardown videos, and this is a double diode vacuum tube. We have the anode, we have the cathode, which is this tube, and then the filament is somewhere inside there. So the anode to cathode capacitance is basically the capacitance between the anode and the cathode, since these two are separated by a certain amount of space. And then from the cathode to the heater, we have a certain capacitance because, well, the heater is inside the cathode. So normally if you have a cathode separated from the heater, then you will have certain capacitance between the two. Now heater or filament, it's the same thing. So in our model we can now add a capacitor between the anode and the cathode, and its value will simply be a parameter, so the anode to cathode capacitance. Now the datasheet also tells us about cathode to heater capacitance, and we can also add this, but for this we will need to add an extra pin to the model. So as I said, I don't want to model the entire filament or the entire heater. I'll simply consider it a single pin. And now we can add an extra capacitor that will represent the cathode to filament capacity. Usually this can be neglected, but it's good to have it in there, so just to make a complete model. Okay, what else have we got in our datasheet? Well, we have some limiting values. So basically, what are the maximum voltages and currents that can be applied to the diode? Now, the currents I will not be modeling, since mostly the current is taken care of by the equation that defines our current to voltage ratio, but I do want to model these voltages. So the first thing that we care about is the maximum negative voltage that can be applied to the diode without destroying it. Now, with silicon diodes, this is the breakdown voltage. And normally it's expressed as an exponential formula, since the higher this voltage applied to the diode is, the higher the current going through the diode. So there's a direct link between the two for silicon diodes. Now in vacuum tube diodes, this breakdown voltage mainly results in arcing. So you'll get an electrical arc between the two terminals. So you either have no current or you have a lot of current going. And the easiest way to model this would be using a switch. So what I'll be adding here is a simple switch that will check the voltage between the cathode and the anode. And based on the parameters, I can set it to turn on when a certain negative voltage is reached. Now we don't just have in the datasheet the negative diode voltage, we also have the cathode to heater voltage. So just like we can get arcing between the anode and the cathode, we can get arcing between the cathode and the heater inside. So there again, we have a maximum value that we shouldn't exceed. And interestingly enough, here we have a certain negative voltage and a certain positive voltage. Now, not all datasheets will have both of these voltages. Usually you'll just have one. But based on this datasheet, we can say that the negative peak is roughly half that of the positive. So this again we will add as a switch, but we will be needing 2 switches for the 2 voltages. And basically this will be the model for the vacuum tube diode that I'll be working on today. Now the only thing missing is how to get the link between the current source and the voltage applied. So let's try something out here. So what we need to do is somehow import this graph into LTspice. And not necessarily import the graph, but rather the function behind it. So the function that expresses how this graph is going. Now one way would be to implement the Child-Langmuir law. Basically this expresses the current that we would have if we apply a certain voltage onto a vacuum tube diode. And this formula is based around the distance between the 2 elements and their surface area. But there's 2 problems with it. So first of all, surface area and distance, well, it's not written in the datasheet, and the only way to find out would be to break open the vacuum tube. Secondly, this law is mainly made for plain parallel diodes, meaning that it's applicable for diodes that are plates that are parallel. And in the case of our diodes, they're basically concentric cylinders. So this doesn't really apply. I mean, it does, but we can't really use it. Now, another thing we can do is try to extract the function directly from the graph. And for that, you can take a random program to extract points from graphs, or you can do it by hand. What I found is this thing. Basically, you take a screenshot of the graph you're working on, get it to fit into the window, double click on some points on it. Now, the more accurately you do this, the better the outcome. And at the end, you will get the points that you inserted on the graph. So what is this useful for? Well, next you take these points and put them into a random spreadsheet program. So either use Google Docs like I'm using right now, or Excel, or whatever other program. And simply you plot in here your values. Now it's important to mention that the graph should start at 0. So when you have 0 volts, you have 0 amps. And now what you do, you take all these data points, insert a chart, and it's still not really useful at this point. But one of the nice things that these programs can do is insert thread lines. Now, again, it's not looking very nice at the moment, but that is because of the type of thread line. So right now the thread line is a linear equation that doesn't really fit our data. But if we go through the various types of thread lines that we have available, so exponential again doesn't really do it. But once we get to polynomial, we get an almost perfect fit. So the second order polynomial equation fits our set of data points very well. And now this thing we can implement into LTspice. So we can take our current source and make it give out a current based on the voltage applied to the diode according to this formula. But we still have one little problem. And that is the data points themselves in the equation. So right now, if we were to start at 0 volts and we replace X with 0, we get a current of negative 1.02, which isn't right. So our equation is good, but it's not that good. And this is down to the way that I basically got my points off the graph. So the more accurately you get the points, the better the equation will fit them. Now at this point, there's 2 things we can do. Either we completely neglect this -1 term, and that will give us an error of around 1 milliamp, or we get our diode to start conducting only when this graph hits 0. So basically figure out what are the solutions to this equation, and to take the one that is a positive value and get our diode to conduct at that point. Or I can try to take out the points yet again to get a better fit. Let me try that for one moment. And now, well, it's a bit better. So my first term is now minus 0.6, so it's a slightly better fit. But I'll still try to get out the solutions to my equation, so simply fill in the free terms. And now we know that if we start off our graph at 0.168 volts, then we will have a very good fit from this equation to our implementation. So let's see how well this works in LTspice. Let's see how well we can implement our datasheet curve into the simulator. And this is basically the final model. So we got all our components in the model, everything is modeled with parameters, so we got all of our parameters here on the left side. We got the parameters defining the internal capacitances, the free terms of the polynomial equation that was introduced here into the behavioral current source, the point at which the diode starts to conduct, so when this equation goes through 0, and this was added as the point above which the diode starts to conduct. So the diode doesn't start conducting at 0 volts, it starts at this particular point, so that we don't have any problems with our equation. Then I added the breakdown voltages, so I took these from the datasheet, and these parameters for the breakdown voltages are inserted into these switch models. So these models have only 3 basic parameters: the breakdown voltage, on resistance, and off resistance. Now these resistances could have also been added as parameters, but we don't really have these resistances in the datasheet, and the whole point of using them is to show us that something went terribly wrong with our simulation. Okay, so time to test out the model. Time to see if this whole thing I've been doing until now actually works. So to test things out, see how well the model works, I created this test fixture. Basically, I'll be applying a voltage pulse to test the filament to cathode breakdown, and also I will be applying a different pulse to test the actual diode, so between anode and cathode. So let's see how these two work. So first of all, let's plot based on the filament voltage. So since we're referring to the filament voltage, not the cathode voltage, the voltage is in reverse. So at minus 150, which is plus 150 from the cathode's point of view, we get our positive breakdown, so exactly the value we got here, and the same thing at 330 negative. And we see that the current shoots from basically 0 to kiloamps, so to thousands of amps. So these switches are working well. And now if we check the current actually going through the diode, and we compare it to the anode voltage, and we look at it the right way around, so the first thing that we notice is that the current doesn't start rising from exactly 0 volts. This is because of our minimum voltage parameter, but the graph itself is basically identical to the one in the datasheet. So let's just take one random point to make sure. So at 60 milliamps we should be having 9.5 volts. And in our simulation at 9.5 volts we get 59.3 milliamps. So it's not perfect, but it's very close. So now that we know that our model is working well, we can try to use it for other diodes also. So the nice thing about this second order polynomial formula is that it doesn't just fit the points coming from the EAA91 diode, it fits the points coming from the EZ80 diode, and also points coming from the DY86 diode. So these are the 3 diodes that I've analyzed with this method. Different types of diode. So we got small signal diode, power rectifier, and high voltage rectifier diodes, and all follow the same rule. So it's safe to assume that most diodes that you will encounter, most vacuum tube diodes that you will encounter, can be modeled based on this equation. So we can use this general model to model any sort of vacuum tube diode. Now, for each of these diodes, I also extracted all of the parameters that our model needs. So if the parameters existed, I extracted them from the datasheet. If not, then, well, I just filled them in with something. So if the model will not have any values, then it will have some problems. So now we need to go from this sort of model implementation to a generic library file. And for that, what I'm going to do is take the netlist. So basically the netlist is how LTspice processes your circuit. LTspice doesn't care about your graphical interface, so how the things are wired in between them, how nicely they are displayed. LTspice only cares about this netlist. Basically what this contains is all of the components, the nets they are connected to, so what the name of the net is, and what sort of parameters or values are associated with said component. So I'll be using my initial model, so without the test fixture. That's because here I didn't connect the Fnet to ground. So now if I go to my netlist, I actually have the net called F. Now I take everything, just to make things simple, and create a basic text file that will be my final library. And here I need to delete everything that is not part of the generic diode model. So all sorts of parameters, all sorts of comments need to be deleted. And what I'm left with is the components and the models for the switches. So to create the final generic model, I need to create a sub-circuit, VTD, from vacuum tube diode, and then put in the names of the pins that will be associated with this model. So anode, cathode, and filament. Then we have the model itself, and we need to end things with ends. Now at this point the model is useless. If you try to import this into a simulation, it will crash because none of the parameters are filled in. So now to create the actual library file, we will make another subcircuit that will rely upon this subcircuit to function. Basically, it's like programming with functions in any sort of programming language. We've created one function called VTD that needs some input parameters, and now we're creating another function that will call upon this previous function. So I can create a subcircuit called, let's say, EAA91 that has 3 pins. So the exact naming now doesn't really matter, just the order in which they are placed. And this subcircuit will call upon a generic component, XU1, that has 3 pins, of course, and is of type VTD, so the subcircuit we just created. And now we need to list all of the parameters. So what are the parameters that the VTD model needs to represent the EAA91 vacuum tube? We'll need to end everything with, again, an ends type command, maybe add some spaces in between just to clear things, make them a bit apart. And now basically our library file is done with one component. So how do we test it? Make sure that we didn't make any mistake in the process. Well, we can import everything into a SPICE statement, we can include it as a library file, but it's still not really useful at this point. We're missing a symbol. So if we go into the MISC category of symbols that comes with LTspice, we see that we already have a symbol for triodes, we have for tetrodes, pentodes, but no diodes. So now we can either create a generic box with 3 terminals, or we can take the triode model, open its symbol, and now edit it a bit to make it look like a diode. And this way we will actually have a nice pretty symbol. So remove whatever we don't need, change the name from triode to diode. We need to save it with a different name so it doesn't overlap with the initial model. So VT diode. And we need our third pin. So we have the anode, the cathode, and from edit we can add a pin that we will call F, and we can place it right here on the bottom. Now another thing we need to take care of is the order of the pins in the netlist. So our first pin, let's call it A, has the first order in the netlist. Our second pin, the cathode, let's just call it K, we want it to be the second in the netlist. And the third pin, which is F, we want it to be the third. Now this is important because we want our symbol to match the order of the pins in our model. So in our model, we have the 3 pins, which are in the order of A, K, and F. And basically this is exactly what we want with our vacuum tube diode model, which we just created now. So to actually be able to use this diode, we need to change its name. So to the name of the subcircuit that we want to be associated with it, so the EAA91. And now, to test it out, we need to recreate the test fixture circuit. So I'll simply be testing out a 0 to 20 volt pulse that rises in 1 second, and that's about it. So just to test the forward voltage characteristic of the vacuum tube diode that I've just created. And moment of truth. So it's a good sign we didn't get any errors. And now if we check the current, we see our nice polynomial equation that, just like before, at around 9.5 volts has 60 milliamps. So the function is implemented correctly, the model is working. Now, what you might notice now, if you look more closely into the graph, is that it seems to be a bit choppy. So we have certain straight lines that have these quite weird points of inflection. And this is because of the way LTspice is simplifying the data so that it doesn't have to memorize so many points. Now this of course can be fixed if we go into the edit simulation command and set a certain maximum time step. So if we set this to, let's say, 1 microsecond, simulation time increases of course, because there's so many more points to calculate, but this time LTspice cannot make any sort of simplifications in the output data. So now we do have our nice curve, which actually looks like a curve. There's no longer straight pieces of line. So now our library contains one diode. Let's add also the other diodes. So basically what I did here, I added the 3 diodes that I extracted the data from. I included a few information about the diodes themselves, so which datasheet I've used, from what year it was. Now this is quite useful in case somebody else ends up using the model and they're not sure why the datasheet that they have doesn't really apply to the model that they've used. So if you use the datasheet from a different year, from different manufacturer, it will contain different sort of data in it. So this is just some good information to have in a generic library. Then at the end, we have a few words about the model itself. So K stands for cathode, A for anode, and so on. And a few information about who created the library and when. So these are just some generic information that is good to have. I mean, everything that has an asterisk at the beginning, simulator will neglect these. And now I also added this include statement, so to no longer have my model pasted directly into the simulation, but rather by using the include statement. So it's a bit more ordered. And the model still works. So my EAA91 diode still has the exact same response. And now we can try out also the other diodes in the model. So let's see the EZ80. Since this is also included into the model, if we run, we see that it has a different response. So for the same amount of current, we have a larger voltage drop. And this basically fits with the datasheet. So for 60 milliamps, we get almost 20 volts for the EZ80. Now, even though this is a higher current diode, it does have a higher voltage drop, but it's also capable of handling these sorts of currents. So now, there's one thing left to do, and that is try to reproduce our initial experiment. So to see how the EAA91 looks like in the simulator compared to the 1N 4001. So let's see that. And for that, I created the setup to reproduce the initial measurement that we've performed. The only difference being that I've added these two capacitors. So 22 picofarads is roughly the capacitance of my oscilloscope probe that I've used to perform the measurements. So let's see how this behaves, starting with the semiconductor diode and compare it to the input signal. And now if we look at our initial measurement, well, it's not that similar. Basically, our problem is with this area. So the point in which the voltage on the output turns negative. Now, the reason behind this is not that there's any sort of problem with LTspice. So it's quite easy in situations like this to blame the simulator. But the problem is actually with the simulation model. So the model that I'm using, I've taken from the onsemi website. And the model was generated by somebody based on the onsemi datasheet. Now, one of the things that is not present in this datasheet is any sort of information about the switching characteristics of the diode. How fast does it switch? The only thing that we do get is something regarding the diode's capacity, but nothing regarding switching time. Now, I did manage to find this datasheet, which is made by General Semiconductor, so a completely different company. And at this point, I think it's important to mention that the diode that I'm actually using is neither of these. So each manufacturer's diode will be slightly different than the diode made by somebody else, even though it's the same name. But anyway, the point is that in this datasheet, we do get this typical reverse recovery time, which is in the order of tens of microseconds. So this is quite a slow diode. Now in LTspice, the parameter that has to do with how fast the diode switches is this transit time. So the transition time between conduction and non-conduction. And in the case of the model that I found, the transit time is set to 1 nanosecond, nowhere near the tens of microseconds that it should be. So before continuing, let's just fix the model. So I'll be creating a new model with some little corrections here and there. And I'll set the transition time to 10 microseconds. And now if I do this and change the diode, of course, we get a completely different result. So we do get this reverse conduction effect, just like we have in our measurement. Now there's one more thing missing, and that is the way in which the diode goes from conduction to reverse conduction to no conduction. So in our measurement we have this nice little slope, whereas in our simulation we have a straight edge. Now again, there's a parameter that has to do with this, and in LTspice that parameter is called soft reverse recovery parameter. And now if we also add this thing at around 0.5, we do get a nice slope. So it's not perfectly accurate, it's not 100% the same thing, but it's better than our initial model. And that's the thing about creating models for any sort of component. You'd basically need three very important things to create a good model. So first of all, you need to have a very good understanding of how the component works. So what does the component do, and how is it operating from an academic point of view? So what are all the parameters that have to do with that component? Secondly, you need a datasheet for the component, since only the manufacturer knows what he did there, so how did he make his component? And thirdly, you need the component itself. So whenever there's a parameter that is not specified in the datasheet for who knows what reason, you need to be able to measure it. And for this, you need the component itself and some sort of test equipment to measure out those parameters. And only if you do these three things, then can you do a good model. It's the same thing for my vacuum tube model. Is it perfect? No, it's not. Are there things missing from it? Probably yes. But let's just see how it reproduces the measurement. So it might be accurate for this measurement, it might not be. But for completely different measurements, I don't know. Until I don't perform the measurements, I cannot say for certain if the model is perfectly accurate. So now let's start comparing with our measurements. So basically both the model and the measurement look roughly the same. There's no major difference between the two. The model starts conducting almost instantly, but not quite, because of the parameter we added to get its characteristic curve modeled, right? So we do have certain problems with the model, but other than that, the measurement and the modeled circuit seems to be working quite well. So just to make sure, I performed one more measurement in which I replaced the 5 kHz sine wave with the 1 MHz sine wave. So first of all, let's see what the simulation predicts. So I'm leaving the same 5 volts amplitude, and now if we look at the output, we see that the output voltage no longer goes down to 0, so there's a nice decay here. This is basically because of the capacitance added to the output of the circuit. And also when the negative voltage starts to rise, so does the output voltage. This is basically because of the capacitance of the vacuum tube itself. And now if we compare this to the measurement, we see a very similar behavior. I mean, it looks basically the same, so the shape of the waveform is almost identical, down to the way the output voltage starts to rise, even though the input signal is still a negative voltage. So we have the same type of shape in both the simulation and the measurement. So basically, we managed to make quite a decent model, and we also created a library that contains multiple components. So I say we did a good job today. So all in all, hope you got some useful information out of this. Leave your thoughts in the comments, make sure to subscribe to be up to date with all my latest videos, and hope to see you next time. Bye bye.